So, astronomers just found a black hole that's breaking the fundamental laws of physics. Not bending them, not stretching them, breaking them. And the craziest part? It's not even trying to hide. It's just sitting there in space, being impossible. And scientists are losing their minds trying to explain it. Okay, so here's the short version before your brain starts melting. We've always thought black holes grow over time, kind of like cosmic cities. You start with a baby star, it collapses, forms a small black hole, then slowly eats stuff until it gets huge. That's how the universe is supposed to work. But then the James Webb Space Telescope pointed its absurdly expensive eyes at the early universe and found one that breaks every rule we know. A supermassive black hole, billions of solar masses, existing just 400 million years after the Big Bang. For context, that's when the universe was still figuring out how to make its first stars. Finding a black hole that big that early is like finding a full-grown whale in a puddle. It should not be possible. Yet there it is, glowing smugly from 13 billion light-years away. Here's why this isn't just space gossip. If this thing is real, and Webb's data says it is, then something about our entire understanding of cosmic evolution is wrong. Not slightly wrong, fundamentally wrong. Because the math that governs how fast black holes can grow, how galaxies form, how light behaves, all starts breaking down. This isn't just an astronomy problem. It's a rethink how the universe works problem. But let's rewind a bit. A black hole forms when a massive star dies, runs out of fuel, and collapses under its own gravity. Think of it like a skyscraper whose support beams suddenly vanish. The whole thing implodes inward until all that mass is packed into a single point. The gravity becomes so strong that even light can't escape, hence, black hole. Usually, the leftover object is a few times the mass of our sun. Over billions of years, it can grow by eating gas, dust, and unlucky stars. That's how you eventually get a supermassive black hole, the kind that sits in the centers of galaxies. The problem is time. Growth takes it. The universe is only 13.8 billion years old, and 400 million years after the Big Bang is practically infancy. At that stage, the first galaxies were just flickering into existence. There shouldn't have been enough material, or enough time, for a black hole to reach billions of solar masses. Even if it ate continuously at the maximum theoretical rate allowed by physics, the Eddington limit, it still wouldn't come close. The math says you'd need about 1 billion years to grow one that big. But somehow, this one pulled it off in less than half that time, possibly a quarter. It's like finding a newborn that already pays taxes. Let's get specific. The black hole in question is designated CEERS 1019, discovered in data from the James Webb's Cosmic Evolution Early Release Science Survey. It weighs about 10 million solar masses, which is smaller than some later monsters, but the fact it existed when the universe was 570 million years old makes it absurd, and it's not alone. Others, like Jazor 3F3 1806, clock in at over 1 billion solar masses just 670 million years after the Big Bang. These are the cosmic equivalent of toddlers driving trucks. Now, scientists can't just shrug and move on, because this isn't one weird outlier. Webb keeps finding more of them. The early universe seems littered with oversized black holes that simply shouldn't exist. It's like opening a history book and discovering skyscrapers in the Stone Age. Either our timeline is off, or our understanding of construction is missing a few steps. So, what gives? Let's break down the options. Option 1, maybe black holes could grow faster than we thought. There's a limit called the Eddington limit, which is basically a cosmic speed cap. When a black hole eats matter, it releases radiation. Eventually, that radiation pressure pushes back hard enough to stop more stuff from falling in. It's the universe's built-in weight restriction on the cosmic elevator. The Eddington limit says you can't exceed a certain growth rate without blasting away your own food supply. But what if, somehow, these early black holes cheated? Maybe they had brief periods of super Eddington growth, or merged rapidly with others. Still, simulations suggest even with perfect cheating, you'd need more time than existed. Option 2, maybe they started bigger. Normally, black holes begin as the remnants of massive stars, maybe a few dozen solar masses. But what if, under the right early universe conditions, massive clouds of primordial gas collapsed directly into black holes 100,000 times the mass of the sun right off the bat? These are called direct collapse black holes. It's a nice idea, except those conditions are supposed to be incredibly rare, and Webb keeps finding too many for that to explain everything. Option 3, the weird one, is primordial black holes. These would have formed in the first fractions of a second after the Big Bang, before stars even existed. Tiny quantum fluctuations in the hot, dense early universe could have collapsed directly into black holes of various sizes. Most would have evaporated by now, but some could have survived, growing into these early cosmic giants. It's speculative, but so was dark matter before we realized most of the universe is made of it. And then there's option 4, which is basically, we don't understand gravity. Maybe our models of space-time at cosmic scales are off. Maybe the way black holes interact with their surroundings changes in extreme conditions. Or maybe, and I'm just spitballing here, the universe is running some weird physics patch we haven't downloaded yet. Because here's where it gets even weirder. These black holes aren't just big, they're active. They're quasars, blasting out jets of radiation so intense they can outshine entire galaxies. That means they're not dormant fossils, they're hungry, energetic monsters consuming everything around them. And because light takes time to travel, when we look at them, we're literally seeing into the past. Webb is showing us a universe that should still be learning how to make stars, yet somehow it's already home to billion solar mass black holes. It's like watching a baby picture of yourself and realizing you're already holding a smartphone, and the data is solid. The James Webb's spectroscopic measurements confirm the redshift values, meaning these objects really are that old, that far away, and that massive. This isn't a misreading or a glitch. It's reality disagreeing with our math. When reality and math stop matching, the math has to change. So let's talk implications. If these early black holes exist, it changes our entire story of cosmic evolution. Galaxies might have formed around black holes instead of the other way around. Maybe supermassive black holes weren't late-stage phenomena, but the seeds that built everything else. That flips the standard model of cosmology on its head. It's like realizing the chicken not only came before the egg, it built the coop and paid the mortgage. But even that doesn't explain how they got so big so fast. You can tweak the numbers, invoke exotic feeding mechanisms, add magnetic fields, turbulence, or dark matter, halos, and it still doesn't add up neatly. The universe, it seems, was more efficient at building monsters than we ever imagined. Now, here's where things get deliciously uncomfortable. If we assume the data is right, then we might be looking at evidence that the laws of physics themselves evolved. Maybe gravity behaved differently in the young universe. Maybe matter could clump faster, because space itself was denser. Picture dough rising before you even add yeast. That kind of physics would shake not just cosmology, but the entire foundation of general relativity. Einstein would probably throw his coffee across the room. Some researchers are exploring new frameworks, like modified Newtonian dynamics, or early cosmic inflation pockets that accelerated growth locally. Others are flirting with extra-dimensional theories, where gravity leaks across dimensions, allowing things to form more quickly. I know, it sounds like sci-fi fan fiction, but when your equations start failing this hard, creativity becomes a job requirement. Here's a fun thought experiment. If time itself stretched differently in the early universe, then growth rates might look faster to us now than they were locally back then. Maybe what seems like 400 million years from our perspective was a much longer developmental window in the early cosmic environment. That would mean our cosmic clock isn't universal. The idea that time might be relative across epochs isn't proven, but it's on the table. And if that's true, then the black hole isn't breaking physics. It's just reminding us we don't fully understand the clock we use to measure it. Let's zoom out for a second. Every big discovery in astrophysics starts as an impossible observation. When we first found galaxies moving away faster than light, people said it couldn't be real. When dark energy showed up, we thought it was a measurement error. Now, both are standard chapters in the Cosmic Handbook. 3I Atlas confused astrophysicists. These black holes are doing the same thing to cosmologists. The universe keeps humbling us. There's also a philosophical side to all this that scientists rarely admit out loud. We think of the universe as governed by rules, but maybe that's just a projection of how humans like order. We write down equations because we crave patterns. But the universe doesn't owe us consistency. When something like CEERS 1019 comes along and laughs in the face of our formulas, maybe it's not breaking the rules at all. Maybe it's revealing that there were never rules, only approximations that work most of the time. And that's the kind of idea that messes with your head at 2 a.m. Because if the universe can casually generate billion solar mass black holes before it's even finished forming its first stars, what else can it do? How much of reality sits outside our ability to model it? We talk about physics as if it's carved into the fabric of space-time. But what if it's more like software? And every so often, the universe pushes an update we weren't told about. Even if we ignore the philosophy and just focus on the science, the discovery is still staggering. It challenges our assumptions about everything from star formation to cosmic microwave background data. It forces us to revisit the early thermal history of the universe. And it gives new weight to the idea that dark matter and dark energy aren't just invisible ingredients, but active players shaping cosmic growth in ways we haven't quantified. Some researchers even suspect that black holes themselves might influence the expansion of the universe. If early supermassive black holes radiated enormous energy into the surrounding medium, they could have heated and ionized vast regions of space, triggering feedback loops that shaped how galaxies formed afterward. Meaning, these impossible black holes might not just be side effects of the early universe. They might be the architects. And that's wild, because it means the thing that breaks our models might also be the reason those models exist in the first place. It's the cosmic equivalent of discovering that your house's foundation was built by the same earthquake that tried to destroy it. So, what happens next? The Webb telescope will keep scanning, pushing deeper into cosmic time. The next batch of data from its ultra-deep field surveys will probably reveal even earlier quasars. Each new one will tighten or shatter existing theories. Meanwhile, ground-based observatories like the Rubin Observatory and future missions like the Nancy Grace Roman Space Telescope will cross-check Webb's findings. We're not just watching history, we're rewriting it as it beams toward us at the speed of light. Look, I'm probably butchering the astrophysics here, but even with my half-baked understanding, the message is clear. We are living in a universe that loves loopholes. Every time we think we've cornered it with equations, it pulls a magic trick. And honestly, that's the best part, because the moment the universe stops surprising us is the moment science dies. Maybe the real takeaway from this impossible black hole isn't that physics is broken, but that it's alive. It grows, evolves, and adapts just like everything else. And when we finally catch up to these cosmic anomalies, we'll probably realize the universe was playing fair all along. We were just solving the wrong puzzle. So yeah, we found a black hole that shouldn't exist, but instead of panicking, maybe we should be grateful, because every impossible discovery is another reminder that curiosity is the only law that never breaks. Somewhere out there, 13 billion light years away, a billion solar mass monster is quietly rewriting our understanding of everything. And maybe that's the universe's way of saying, you're not done learning yet. Keep looking up. Keep asking dumb questions. Because if the cosmos can build a black hole before it can build a galaxy, then maybe, just maybe, the impossible is a lot more common than we think.